Hello, welcome to Broadcast Servers, Replacing Videotape Recorders. This is a presentation for the CUMPS 268 Broadcast Communication Systems course. So, first thing, let's take a little history lesson back at 2-inch videotape recorders. So 2-inch videotape recorders were huge machines like this one. If we take a look at over here, here's the reel. The reel weighed about 40 pounds, and you had two of these suckers, and this whole machine weighed about 1,500 pounds. And it was all pneumatic, and pneumatic means that it was air powered. We had the head was over here. It rotated at about, I can't remember, it was just before my time. These ones kind of died in 1981. They were sort of being phased out. 1-inch videotape recorders were smaller. They're 1-inch was the width of the tape, and you can see they're a much smaller, sort of a desktop unit. This is a portable one. We actually had two reels on top of each other, and this would weigh probably about 40-50 pounds. This would weigh about 120 pounds. 3/4-inch videotape recorders. This would be an editing one. We have the edit controls over here. We'd have another one that would be a play machine. In between would be a controller, and the width of the tape was 3/4 inch. So 2-inch tape was 2-inch wide. It was huge tape. And this one ran cassettes, 3/4-inch cassettes. Right now we have 1/2-inch digital tape recorders. Sometimes we call them Betacams, but they're not really Betacams. These are digital recorders. These are the ones that we have in our lab. Video servers replace videotape recorders. They use hard drives instead of tape. They're digital recorders, not analog. They're file-based workflows, so we can treat the video as a file. And we need terabytes of storage and needs high-speed network connections to it. Here's what a video server looks like. It looks like just any other server. This one says video server, so we know what it is. Parts of the server, we have a CPU, the external data bus is important with the CPU, memory, I/O bus, and hard drive. So we'll take a look at the different parts of a server. And this is what a server looks like. We have a lot of fans on it. You guys have done Lab 22, which takes apart a server, so you have an idea what an old server looks like. New ones look similar to this. CPU is the fastest part of the server. CPU factors which affect the performance: the number of processors, the processor speed, data bus size, data bus speed, and internal cache size. That's supposed to say SCSI, but I think size. A number of processors. The number of processors only affects performance if the application is able to use multiple processors. So if you ran Windows on a server with 32 CPUs, you would not see any performance increase. If you ran a database, you would see a difference because the database is aware of the CPUs. Something is that we can have CPUs and we can have cores. Right? So CPU is a physical device. The core is internal. A processor speed is measured in gigahertz. The larger the number, the faster the CPU can perform. So if you have a 1.6 gigahertz machine is slower than a 3.4. So the bigger the number, the better. Some CPUs like AMD's perform parallel operations and have a processor speed that is relative to the gigahertz. And there's tests to measure relative performance. One of them in the Linux world is called BOGO MIPS. Right, so you can, whenever you boot up a Linux server, one of the things they'll do is give you a speed rating in BOGO MIPS. One BOGO MIP is equivalent to a 8086 processor, which was the original XT, and I believe it was 6 megahertz. So one BOGO MIPS is equivalent to 6 megahertz. Data bus size. The size of the data bus is measured in bits. The data bus transferred data in parallel. So the larger the number of bits, the more data that can be passed at one time. So a typical data bus size today is 64 bits. So some of the older days it was 32 bits, and now it's 64 bits. So bigger the data bus, the better. Data bus speed is how fast can you transfer internally. So a CPU manipulates data internally at its processor speed. To talk to the outside world, it talks at the data bus speed. So the faster the data bus speed, the quicker data can be transferred through the computer components. Internal cache size. Cache is a term used to describe storing the most commonly accessed data in a faster than normal memory inside the CPU. So the CPU reads the expensive cache memory, which is internal, faster than it reads the outside world. So what we want to do is they have a caching algorithm. It's a magic formula. And what it does, is it takes the most commonly accessed data and it stores it inside the CPU, so it goes faster. So the more cache you have, the more data you can put in it, and the faster your access is. It doesn't have to go to the outside world. Memory is external to the CPU. There's two main types. External cache, it's expensive and fast. It used to be called static RAM, SRAM, and you have a little bit of it. And then you have dynamic RAM, which is the inexpensive and slow, and we have a lot of that. So if we look at this diagram here, we have the CPU on top. It's going to have some internal cache. Then you're going to have an external cache, level 1, and level 2. This used to be called the north and south gate. And then you have your RAM memory. So it's kind of a pyramid that says RAM memory is pretty fast. We'll go right to the bottom. Mass storage, like hard drives, is really slow. RAM is faster, so you'll have some RAM cache, so you'll store the most commonly used instructions and data in RAM memory, and it's faster than a hard drive, about 1,000 times faster. Then what happens is you take in RAM, you store the most commonly used data in cache RAM, which would be in your north port. Then what happens is you take the most commonly used instructions and data in level 2 cache and you store it in level 1, which is typically inside your CPU. And what happens is the price, this is cheap, this is more expensive, this is a lot of dollars, and this megabucks because it's part of the CPU. I/O bus, the interface to the peripherals. The peripherals are your hard drives, network cards, graphic card, which is not important in a server because it doesn't need a graphical user interface, a GUI. A typical example in the lab, we use a keyboard, video, mouse switch, and we just switch between the servers. So we have a CPU is connected to our data bus, which goes to memory, is connected to, and then we have our I/O devices. And the I/O devices are the interfaces, and they have their own speed too, and they're a little bit slower than everything. So I/O standard interfaces is SATA, serial ATA, up to 6 gigabits per second. That's what's typically used in a PC or a laptop. PATA is the older parallel ATA, sometimes called enhanced IDE. SCSI is a small computer system interface that someone scribbled on here, and that it's comparable to SATA for performance, and it's more complex, but it has some advantages. Some of them are it's hot swappable. So SATA interface looks like this. We're all familiar with it. We have our connection here and a connection here. One is power, one is data. PATA has this 40-pin connector, and then you have some jumpers that you'd set one up as master and another one as slave, because if you had two hooked together, one would be master, control the bus, the other one would be a slave to it, and you have your power connection. So this is legacy, means it's old. SCSI has different interfaces. This is the really old one. It's like a DB25, and then we had another connector like this, which was very popular, and the latest one is a sort of a mini SCSI connector. Hard drives are mass inexpensive storage devices. The slowest part of the server must access terabytes of data. Typical hard drive specs are 4.5 millisecond seek time, 60 megabytes cache, and then 60 megabytes per second sustainable speed. So we have a problem with this speed is not that fast. Plus the seek time, how long does it take for the platter to turn? Right. So if we want a 6 terabyte server, we start looking at the hard drive requirements. So if we want raw video at 8 megabits per second, we need 1,000 hours of playing time. For a 6 terabyte server, we could store 1,000 hours at 8 megabits per second. 12 megabits per second, 700. Now we're talking compressed high definition here. 25 megabits per second, now we're getting some decent high definition TV, and we're running at only 350 hours for a 6 terabyte server. How to speed up hard drive access? We increase the dynamic RAM. We add more, and what it does is we cache more data in RAM rather than access from the hard drive. So this is an easy way to do. We can use an array of hard drives. We can spread the data over many drives. We can read, write two drives in parallel. The latest one is to add SSDs, right? So we can add an SSD hard drive, which is a solid state drive, and that'll speed it up immensely. So, but the problem with SSDs is they're not stable enough for servers. So it's very rare that we will use SSDs on a server at this time. They don't have the stability and the reliability at this point. Another way we can do it is we can use a redundant array of inexpensive disks, which is called RAID. Sometimes it used to be called that. Now it's called a redundant array of independent disks. So what we have is looks like a network attached storage drive. We've got 5 hard drives in them, and what we can do is combine those hard drives into one RAID array. Different levels of RAID systems provide speed increases in read or write time to hard drive array. We can increase the overall hard drive size, and it also adds fault tolerance. So here's what a RAID array looks like. This is one array going down here. It's 24 drives that are combined in a specific combination to create some unique characteristics. So very first, what they do with RAIDs is they have them numbered. So RAID 0, data is striped across several disks. So the idea is that we have one disk drive here and we have one disk drive here. So we stripe some data here, and then the next block of data we put here, and then we keep going back and forth. So it speeds up reads and writes because we're only taking a little bit from each drive. All disks combine size to form one larger virtual disk to the operating system. We call it a volume. If one drive fails, we lose all data. So if you need a bigger drive, you can start adding disks onto this and you can increase the RAID size, but we have no fault tolerance here. RAID 1 is called mirroring, and mirrors the drives for reliability. So everything that's on this drive is mirrored on this drive. So we have 2 drives. If this drive fails, well, this one still has the data. We read speed twice as fast because what happens is that we can read some data from drive 0, disk 0, and some from disk 1. Write speed is the same as one drive. Size is the same as the smallest single drive. We don't get an increase because we're just mirroring the images. RAID 2 is not used, so we won't talk about it. RAID 3 is not used. RAID 4 rarely used. As a matter of fact, I can't even remember RAID 4 being used, so we'll just skip it. RAID 5 is used. What happens is that they stripe across all of these drives. So we have 4 drives, stripe across data, 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 and then what we do is we do a logical OR on this one of this data. Then what happens is it staggers again, the next block of data here, here, and now we have our parity information here, and then we have our data. And then we keep striping all the data across, and we keep moving the parity. Now what happens is that it holds more data for the same number of drives, and if one drive fails, we can recover all of the data from the information that's stored on the other 3. Right? So if this drive fails, there's enough information here that we can plug a new drive into disk 3 and it will rebuild the RAID array. So we have our fault tolerance. So it gives us a speed increase, it gives us a bigger drive, and then it also gives us fault tolerance. RAID 6 is similar to RAID 5, but 2 parity blocks. So now with the things, we got 1, 2, 3, 4, 5 drives. If 2 drives fail, we still can recover. Right? So it has redundant parity on it. So what we see typically today is RAID 5 and RAID 6. RAID 10 is actually made up of RAID 0 and 1. This is my favorite one. I like to use it. We get increased speed for read-writes. We get fault tolerance if one drive fails. We have mirrored images. So what we do is we create a RAID 0 on 2 drives here. So now we have our size, and we have a speed increase because now we're reading 2 drives at the same time. We do the exact same thing here, but these RAID volumes are mirrored. So if anything fails here, this has all the information. When we go to do a read, it's reading from 4 drives, so we get a huge speed increase. So we get fault tolerance and speed increase. This one is very popular also. So we see RAID 10 and we see RAID 5 or 6. So improving server performance and fault tolerance, we can use cluster computers, a group of computers that work together closely as though they are a single computer, right? They're connected through fast LANs, improve performance and or availability over that of a single computer. So here's an example of a cluster computer. One of the things that if you walk into a data center, this is what a data center looks like, is all you see is a bunch of servers, individual servers, and then how we group those servers together will determine what their application is. Categories of cluster computers: high availability clusters, also known as fault failover clusters, and they're concerned with fault tolerance. So with these guys, what happens is that this would be used like for the banking industry. So what the banking industry does is we want to make sure that they're up 24/7 without fail and we don't lose any data. So you set up your cluster of computers as failover clusters. If for some reason any computer or server in that cluster fails, it's going to fall over to another one and we're not going to lose any data and the system will keep running. Load balancing clusters, they're balancing the workload across servers. So example is a web servers. When you go to a website, you might be talking to 100 servers, and what they'll do is they'll have one server is going to take control over the load, and what it's going to say is this server is underloaded, so you're going to go to that. So sometimes what you'll see is instead of going to www.site.ca, it might go to www1 or www2 or number 3 or 4, and that'll happen in the background. You won't even notice it. Grid computing, servers are geographically diverse. They don't trust each other except for one job. Used for computing that doesn't need to share data, just works on one portion of a problem. SETI was an example of that. That was a search for extraterrestrial intelligence. Right. So another one that's going on right now is called folding. And what folding does is it use a portion of your computer, like you could be the laptop or your PC, and you run a folding program and you join a cluster that's researching disease control. So as example, I have at home, I'm running folding, and I was part of a cluster that was trying to find out one part of the COVID-19 virus. Another time it was looking up for some cancer information, right? So it's a way of sharing information on your computer into scientific data. A storage area network, a SAN, it's an architecture to attach remote computer storage devices, disk arrays, tape libraries, optical jukeboxes. The devices appear as if they were locally attached, and it puts all the storage of data in one area. So here's an example of a SAN. It's just a bunch of hard drives together, and then they'll be in some sort of frame, and the frame will be talking to the rest of the world, usually through some sort of interface like SCSI or fiber channel or something like that. Network attached storage is a file level computer data storage. So we have our backup server in the lab was a NAS network attached storage, and what happens is the performance can be increased in a server because the NAS is doing all the file serving and not the computation that the server is responsible. It could be doing other processing. So here's an example of a small NAS over here. We have a small one. We got two 2 terabyte hard drives in it, and they're mirrored together. So we have our fault tolerance and that. And here's an example of a larger NAS that would be used in a data center. Broadcast video server specs. They're called play-to-air servers. They're a cache for satellite ingest. They're graphic storage, weather systems, remote trucks, extra channels, and DTD broadcasts. So this is where they would be used. Here's an example of one. So what would happen is that you would have inputs from a program source. Program source could be satellite. It could be a videotape recorder of some type, SDI. You might have remote workstations attached to it, a non-linear editor. A linear editor is the term that's used for editing videotape. Video is all on a linear line. So if you wanted to go to a new shot, you'd have to rewind the tape to the beginning of it. Non-linear is file-based. So what we could do is we could basically pick up anywhere on our hard drive that shot that we want to look at, the clip. Then it could be attached to a network storage device. It could be storage area network or network attached storage. What we'd have is SDI and composite outputs. We can have audio channels connected up to it. And then we can have some control channels also if you were doing automation systems like master control. Typical broadcast server specs, so you can have video inputs, SDI, HDTV, composite, outputs also. So they'll look like a regular server, except they're going to have these extra inputs and outputs on it. And also you can have AES digital audio or analog audio channels for every video channel. So we were talking about if we had 700 hours of program storage at 12 megabits per second, we would need 6 terabytes of storage. So right off the bat, we need lots of storage. We need frame synchronizers for recording wild sources like tape and satellite feeds. So when tape and satellite feeds come in, they're not synchronized to our house system. So we have to have a special synchronizer. It's called the frame synchronizer, so that we can actually use these sources and synchronize them to our station and that. And typically we're going to run at gigabit Ethernet or higher, 10 gigabit and that. Typical redundant power supplies and cooling fans. So if one power supply fails, what happens? It'll automatically switch over to another one. Hot swap drives with easy front access. So we'll have hot swap. Usually that means they're SCSI drives. Double fault tolerant RAID 6 protection. RAID 5 minimum, RAID 6. So that way if one drive or two drives fail, we don't lose our data. An alarm system for faults, right? Now, Blackmagic Design is a company that really revolutionized the broadcast industry, and this is what their broadcast video server looks like. It uses plug-in SSD drives. They're the first ones to access it, and there's only a few SSD drives that will actually meet the specs, right? And so one of the things they, as you can see, is a very compact design. We have one of these in the lab, and you'll work on it in second year. We're also moving to IT storage. So you'll see that in the racks, a lot of the stuff is saying, why should we reinvent the wheel when we have all this IT equipment that's relatively inexpensive? What we'll do is we'll just add a few expansion cards on the back that will allow us to do our broadcast interfaces. Now, when we go to IT-based, one of the things is now everything is PC-based interfaces. We connect through the internet. And so our interfaces have changed too. In the old days, we used to have manual controls like this, and now like this over here. Nowadays, it's all going through keyboard and your keyboard and your display monitor touch-sensitive screens. So if you like this video, subscribe to my channel and hit the like button. And if you have any interesting comments, put them in the comments section. Thank you for watching.